any questions from yesterday's discussion? Well, good news is I printed out a bunch of problems we're going to work on here in just a second. Here's where we ended yesterday, where I said the neat thing about epoxide rings is you can open them and form dials. Here you can see when you do it in the presence of an alcohol, you form and put on an ether group. Let's look at base catalyzed opening of an epoxide. So looks real simple, looks SN2-ish in that it's concerted. I see both things occurring at the same time with those curved arrows. The hydroxide attacks and opens the ring. The dial is obtained after protonation of the alkoxide with water. Add some water and protonate that. As I mentioned the other day, a 3-membered ring has lots of ring strain. It says here an epoxide is higher in energy than an acyclic ether. So that means one that's not in a ring. Here would just be hydroxide hitting that and that leaving. And so this is so much higher in energy, not much of an energy of activation. And here's a lot of energy of activation, presumably the same product here. So at 25 kilocalorie per mole ring strain, release of the ring strain makes the opening of an epoxide thermodynamically favorable, or 105 kilojoules. So here's our epoxide ring. Here's something like hydrogen bromide or hydrochloric acid. Oxygen gets protonated. Now it becomes a good leaving group. Here's an SN2 event, and we're back to this halohydrin we looked at before. So yesterday we saw that a halohydrin can be converted to an epoxide. The halohydrin initially formed reacts further with the hydrogen halide to give a 1,2 dihalide. This gets protonated, the halide slams into there, and there's how you get the dihalide. So here's the important thing that I want to get to out of this chapter is regioselectivity. So here is a epoxide, here is acid catalyst, here's an alcohol. So this thing's going to get opened up, and we're going to form an ether and an OH group ultimately. And here's the product, and we can see that this alcohol group hit right there, eventually protonated the OH. But here's about the same thing under base conditions. So here is ethoxide in some ethanol, here's acidic ethanol, and we see that it goes to this carbon. So we have control. Acid catalyzed to get one product, base catalyzed to get the other. So why is that important? Well, if we do a Grignard reaction on an epoxide ring, we don't get the ether and the OH. We're just going to get the OH and add an alky group. So here we see that group hitting right here. Strong bases such as Grignards and organolithiums open the epoxide ring by attacking the less hindered carbon. So let's go back and look at the base, the less hindered carbon. So I kind of like to think of this as anti-Makarnikov. This is Makarnikov. Now we can't say the rich get richer with the hydrogen content, but we see 2 hydrogens here and perhaps none over here. But we could have a hydrogen and have just one alky group. We don't necessarily have to have a tertiary carbon there. And so this would almost be like, well, that's what I find it analogous to, if that helps you remember. And I think the concept with the acid catalyzed, in the transition state, you form almost like a carbocation, and you want to form the positive transition on this more substituted. In the base, that never occurs, and it's strictly steric hindrance. All right, so just steric hindrance, it's going to want to go there. There's where it goes. So I talked about JB Weld. Nobody knew what JB Weld was. Maybe just epoxy glue. You buy the 2 tubes and you mix them together with toothpick glue stuff. Now, how many of you ever heard of bisphenol A before? Bisphenol A. You have? Yeah. You know, when you buy Campbell's soup and you open up the can, you know the metal is nice and protected. What's it protected with? Some coating that has this as a plasticizer. So this has been in the news for the last 15, 20 years as a potential carcinogen and one of those things where modern chemistry is so nice until you find out it isn't. But here is an epoxide. Here's this thing here, and we can see this thing called a pre-polymer. The earliest glues were made by carbohydrates and proteins. If you glue a musical instrument together, you use this thing called hide glue, made from hides of animals. And it's kind of nice. You can heat it up and it gets soft, so you can take things apart. And it's also nice in that it's very rigid. It doesn't creep, and so it sounds better on a violin or whatever. Epoxides polymerize in place so they match the shape of the joint perfectly. Or you can make a big welded type bead with epoxy resins. And these things add and do their thing. What is the correct IUPAC name for this thing here? Find the longest continuous chain. Do I want to number it that way or the other way? Which has priority? The alcohol does. Yeah, so we want to go this way. So that means, that can't be right. 3, 4 epoxy, 3 methyl pentanol, 3 methyl, 3, 4 epoxy. What's the difference between 1 and A? Pardon? I don't know, the book says this is the right answer. I think E comes before A. I don't think it's an alphabetation issue. I think this always gets tacked on to the carbon chain as a whole unit. We might have saw that somewhere. Any questions on naming? No, we didn't. Probably not, because I'm probably nice that way. Of course, what I'm going to do on a test is this. Name this. So let's just see how well I can do on this. Now, something I'm going to do which hardly too many students do. I'm going to look at this and say whatever it is E, right? That double bond, the high priority groups are on opposite sides. And then the next thing I might want to do is go 1, 2, 3, and say which has priority, a double bond or ether. Given this lineup, I would just go with this one because it's telling me about the stereochemistry. 1, 2, 3, 4, 5, 6. So we've given the double bond priority over the ether group. E, 4 isopropyl, 4, 5 dimethyl, and 4 isoproxy. I had trouble the other day when I gave you an ether like that and I messed it all up. Hex-2-ene. So we can review naming ethers. We named the alky group and we named this as an alkoxy substituent. All right, easy enough. Cyclopentane. Let's just call this 1, 2, 3, 3 ethyl, 1, 2 epoxy. Cis, what does that mean? So I already got dashes. I'm going to turn these into wedge. I like drawing wedges. I don't like hatcheted wedges or dashed wedges. Which now that looks kind of weird. That's got to be that thing there. So this is why you came to class today, to get the synthesis questions. Provide the major organic product of the following. We might have to use the last thing I went over. What do we form? There's almost like 3 steps. What do we get after step 1? It starts with the letter E. If we get an epoxy, now how do we know that? What's this? This is, let me just draw it out here. That'd be acetic acid, but I see 3 oxygens. So this is a per acid. So that's our clue. We get an epoxy. Then the next thing to look at is this thing here. What is this? Sodium sodium, and sodium's just kind of a spectator atom. We don't care about that so much. So we're going to open the ring. Acidic or basic conditions? What? Yeah, basic. The sodium alkoxide, yeah, that's maybe a little stronger than sodium hydroxide. Okay, so now where does it open the ring? This carbon or that carbon? The outside one? The less hindered. Bam, that hits there. You got a bonus today, you get the mechanism. All right, so, and then of course this thing, it's just gonna protonate that. So once again, a per acid. This thing protonates this. Then what happens? There might be one deprotonation step missed, but I wanted to compare and contrast this to the last one. So almost the same thing, but instead of sodium methoxide, I just have methanol in acidic conditions. So we still open the ring, we still form an ether and an alcohol, but it's in a different spot. Now we're all warmed up. We know we formed the epoxide. CH3MgBr, what's that? Yeah, it's a Grignard reaction. So I always tell students, when you see a Grignard, you got a carboanion. Now is this acidic or basic conditions? Grignard chemistry. All high-powered organometallic chemistry occurs in basic conditions. Yeah, this is like the corresponding acid would be methane, an alkane, the weakest acid known to mankind. This has got to be about the strongest base. All right, so based on the end of today's lecture and the first two example problems, where's this going to hit? There or here? Slide said the base just hits in the least hindered. I said when the acid, there's almost like a transient carbocation in the transition state, and it hits there because then you have a secondary carbocation instead of a primary. Or we develop a positive charge, and it's better on a secondary carbon than a primary carbon. So that means this thing's gonna slam in there. So, and then we have this thing, which gets protonated. We'll skip the Williams ether synthesis. Provide the major organic product for the following reactions. So the mercury acetate followed by sodium borohydride. What do you remember about that from the fall? It stopped carbocation rearrangements. That's not an issue right now today. But when we did, say, acid catalyzed hydration of a double bond, we got Makartnikov regioselectivity, and that normally put a hydrogen here and the OH there. So now we're not doing it with water here, we're doing it with an alcohol. So I'm gonna just, you can see we now have two hydrogens here. So the rich got richer and the poor stayed poor. What do you think about this question? I'm gonna play games with you. I'm gonna say it at 200 degrees. Of course, this gets protonated. All right, whatever. So at high temperatures, we get this elimination. This would be acid catalyzed dehydration of an alcohol to an alkene. But in the ether chapter, under proper conditions, what do you think we form? In the ether chapter, so this would be the bimolecular dehydration of an alcohol to an ether. And the book says it's done industrially. And industrially, they can, if they get this mixture, they can just churn it around and recycle it. But in the ether chapter, you can look at the slides. One of them showed the bimolecular condensation. There's the condensation coming out.